Okay, got a little bit of a late start. I had a meeting that turned into complete chaos. But yeah, getting started now on VDSO. So let me see. I'm gonna keep this space for reading, so I don't have to relay out things, and then I'll use this space for the VDSO stuff. So, where do I want to do this? Okay. Okay, git init this guy, and then I'm going to mkdir vdso, and then in here, I'm just gonna start fleshing out the commands that we're gonna run. So, well, actually, you know what? We'll say notes.txt or .md, or we'll do readme.md since it readme.md vdso. So we can just ask AI here, hey, I think it stands for virtual dynamic shared object. Yep, that's exactly what it is. Good job, AI. Oops. Why? Okay, it's small kernel provided shared library that is mapped into every user space process to let certain kernel services be executed without a system call. I'm going to rewrite this in my own language. So, certain, the problem that, what to say up front, certain syscalls, certain syscalls take more time than they, how do I say this, are take more time than they should because of syscall overhead. VDSO was introduced to, let's fix this. I wish the GQ thing worked on this. Maybe if I move it like this, will this work? Let's bring this to like 80. Where are we at here? Oops. 80 is here. So if we do that, no. Let's ask another AI. In lazy Vim, how do I enable GQ to hard break lines at 80 chars? Come on. Feed that into Vim. Huh? Remember that lazy vim is based on neo vim, so I need commands that are compatible with the cancel Lua or use the vim compatible features of neo vim. God, I hate AI sometimes. vim.opt.textWidth. Okay, fuck it. We'll just manually break it. I'll just add this in between here like that. There we go. Okay. Certain short syscalls take more time than they should because of syscall overhead. We just was introduced to allow processes to call functions provided by the kernel for these syscall making the kernel does this by mapping in a virtual DSO that provides a number of symbols for functions that return these values. glib, glibc, so just say libc in general. The first thing is vim main.c, or we'll just quit here. Jump over to VDSO. Oops. Jump over to VDSO. Vim main.c. We'll just say main. Zero. Oops. And then we do GCC that's annoying. I want to see the actual markdown code blocks. Let's try Gemini this time because ChatGPT is garbage. In lazy vim, setup that comes with Omarchi based on NeoVim. When editing markdown files with code blocks, it hides the lines. How do I have these shown? There we go. permanent fix. I really need to spend some time just learning lazy Vim and NeoVim because I knew how to set up my Vim config with just regular like Vim 8, Vim 7, Vim 8. And I definitely would prefer to write Lua than Vim script, but sometimes this shit just it's not well like known, documented online, like how to change these things, or at least I haven't spent time reading the documentation, so I need to do that. Just want some simple ass setting of Vim config. Shouldn't be this hard. The only setting that stuck when I relaunch Neo in Vim is the color column. The code blocks in the MD file do not show, and I can not type to force wrapping at 80 calls. So stupid. Oops. I don't want to freaking config auto commands. Okay. Come on. Conceal level. So I'll take care of that. Come on, stop resetting my scroll. So stupid. Markdown. It's just so annoying. I give up. I guess I'm just gonna have to spend time learning NeoVim, just reading the documentation, because AI is incapable of presenting a config for doing something as simple as not concealing the backticks. In the meantime, I'll just run these commands manually, which were set conceal level 0. Even that didn't work now. Very sad. Anyways, why is that? This lazy Vim just does too much. I just want a regular ass Vim. I do not want like all this nonsense. Anyways, let's continue. Oh, this is so annoying. I just want a regular Vim. Okay, let's go into config and Vim. And here, Vim and Net, Lua, we're just going to delete all this stuff except for the color column, which actually worked. Let's go under Lua maybe. Get status in here. It's not a get directory, cd Lua. And then here, plugins. And then we have maybe a markdown Lua, this thing. That thing's going away. CD back to here. Config. Auto commands. Yeah. So we're going to go down here and say tree dot, do not have tree. We can say lt dash 9 dot, what is it, L9? Yeah. And then find dot dash type F, and then pipe that into while read line, do echo $line, cat $line, done. So this is all the config. I'm going to give this all to this is all of my config for lazy Vim, neo Vim. I want to do two things. One is to disable the concealment. What is it? How do you spell this? Conceal element of the backticks in Markdown code. I want it to show me all the characters. In fact, if you disable all of that garbage where it replaces headlines with number, that would be preferable. 2, I want to be able to hard break lines at 80 calls with GQ. Then just give it everything. Hopefully you'll be happy with that. Yes, I want to disable it. Okay. Plugins, UI. Great. Nope. Config options. There we go. No, I don't want to do that. Uh, go back into options. And then I might want to grab the init. And put that in here as well. Okay. No, it didn't work. GQ brace. Yeah, I actually do prefer that. Great. This helped a lot. However, I still cannot break lines with GQ. I think it is because G is mapped to something that pops open a window. GW. Okay, I can use UW. Alright. Alright. Just feeding all of the configuration into ChatGPT got me there. But even still, it's like GW, which is like, why can't you just do GQ like it used to be? Anyways, so certain short syscalls, brief, that only take a brief amount of time, like getting the current time. Take more time than they should because of syscall overhead. VDSO was introduced to allow press to call functions provided by the kernel for these syscalls. There's actually okay, let's go over to the VDSO directory. Main C is just a return 0, GCC O main C, LDD main, and then say what is the GCC flag to disable linking against libc? No standard lib. no default libs. All right. Skip. Yeah, it'd be skip. So we can see it's an elf file, and then we can use read elf. We do -s, yeah. Oops. Let's give ourselves a little bit more space here. I'm going to close out of these. why is that VDS dot dot dot? I don't like that. Maybe if we do cap S. That's section headers, symbols. Demangle. We'll do all dash A. Why not? See what that gives us. So this is all. There we go, wide. Wide. W, capital W, S. So we can say WS. That. Alright, I'm going to take a quick break and then I'm going to play around with Ghidra and see if I can get that to actually disassemble some of these VDSO things. Cool, I'll be right back. All right, let's get Ghidra installed. I've never actually used Ghidra before, so this is new to me. Ghidra. Let's do Pac-Man S Ghidra. Cool. Sudo I know it's Java based, or at least it was at the time that I looked at it a couple years ago now. So it might require the JVM to be installed. I mean, to be entirely frank, I've never even launched it before. I saw this from the NSA, and I was like, maybe I'll let this one cook in the open before I install this a little bit, but it seems to be well trusted by the industry. So Ghidra, can I do this on Linux vdso.so? I agree, yes. Thank you very much, NSA, you're the best. It's not a project file, okay. Cool. And it actually says NSA reverse engineering software. This is the help. SRE is software reverse engineering. I like that better than site reliability engineer. This framework includes a suite of full-featured high-end software analysis tools that enable users to analyze compiled code on a variety of platforms, including Windows, Mac, and Linux. Capabilities include disassembly, assembly, decompilation, debugging, emulation, graphing, and scripting, along with hundreds of other features. Ghidra supports a wide variety of processor instruction sets and executable formats that can be run in both user interactive and automated modes. Users may also develop their own Ghidra plugin components and/or scripts using the Exposed API. In addition, there are numerous ways to extend Ghidra, such as processors, loaders, exporters, automated analyzers, and new visualizations. In support of NSA cybersecurity mission, Ghidra was built to solve scaling and teaming problems on complex SRE efforts and to provide a customizable and extensible SRE research platform. NSA has applied Ghidra SRE capabilities to a variety of program problems that involve analyzing malicious code and generating deep insights for NSA analysts to seek a better understanding of potential vulnerabilities in networks and systems. Cool. This looks interesting. There's like a little book that comes with it. Let's close that out. New project. Non-shared project. I don't like to have to create a project. I'll create it in source, GitHub, experiments, VDSO. Finish. Cool. File, open, import file. This would be under source. Oops. Go back. Source. this? Yes, the elf language. Okay. Okay, so if I double click on this, can I do open in default tool? What is the linking symbol table? This one. So they have these underscore VDSO time. And it just calls that thing time. Oh, because it's time here. Well, at least this function's a little bit simpler. So time is a function that takes a time t pointer. Can I close out of that, or will that cancel? Move that over there. Which is interesting. The argument is named underscore timer. So tvar1. Okay, let's read through this. So we got a T var 1 and a PU var 2, which is an undefined pointer. Then we take a reference to dat, and then if that at this address is not equal to that, then we take a reference to this other one, and then we say, okay, time t pointer is pvar2 plus this offset of 28. So this is like determining where the main location of memory is, and then this is saying, hey, go 28 bytes off of that, and that'll be a time var, which is a pointer to time t. So this whole thing is to find like the pointer to the time t, and then we dereference it. Okay. Once we dereference it, it'll copy it into the stack, and then if the original timer that's passed in as an argument is not equal to null, then we dereference it and write in the value. If it was equal to null, then we just return it. So this is like a optional, like, hey, write the memory over here. I don't want to deal with the return value. Global starting with maybe this is syntax for relocation relative to this location. I'm not sure. What else can we do on this thing? So we have a program tree, text, so this is a function. Little note. So these are labels, right? If I go to labels here, no, they're not labels. Let's ChatGPT here. Auto-generate label, so it's not something that's in the binary. Okay, it's saying that this is the address in the program's address space. So let's try reading from that address. So we can do the same DD, but instead of here, oops, just put this down here. We'll give it time. And what is its width? Its width is a time t, which, can I go to definition of this? Maybe if I go here and say man time t, the actual time t type. Vim test.c time t main time t foo. Pound include time.h time t under time t. It's a second since epoch. We'll say how many bytes is a time t on AMD 64 latest Linux kernel. Eight bytes, that's what I thought. So it's going to be one of these addresses, either this one or this one's going to be PUVAR2 plus 28. So let's go ahead and grab this address. Python. Let's say FB000 plus 0x28. So we're going to skip to there. It's very low compared to where the VDSO is. And then we're going to do another one. We'll call this one time.1, time.2. And it might be relative to the actual ELF itself. So I might need to add an additional offset there. But this is going to be, instead of FB, it'll be FA. here. Okay, let's run those. Oops. Okay, I'm getting input output error, so I'm guessing that's not the correct range. So I think we have to add, if we do a history grep dd grep mem. Okay, so we had done this skip here. I think we need to add this as an offset. Oh, come on, stop being stupid. Oh, so annoying. Alright, that's, the other one was FB. Okay. So let's do time 1 will be the FB one here. Still input output. Oh, it's because it's count 8. Yeah, that's right. BS1 count 8. Yeah. Nope. Still input output error. Well, if I do history here, can I at least do this? And we'll say dot temp. That one had no issues. Huh. I should correct all of these references to VDSO. VSO as VDSO. There we go. I already did this. This is the same exact expression here. Why would they do that? Minus video what? I think what I'll do is I'll just show the decompiler output. I think that's cool enough. Instead of actually trying to figure out where in memory this is. I mean, I wanted to figure out exactly the place in memory that it's reading from, and then show that those bytes are getting updated as time progresses to show the time. I mean, that would be pretty cool. But computing these offsets is just annoying. Like, where is it offsetted from? Alright, well, let's try this thing. See if that works. I doubt it will. Hey, it did. what I really would like to have is like something that could just show me main memory and then allow me to navigate these pointers as the process is running. Like I could just go to that offset, see the instructions running, and do the dereferencing and everything through like a GUI or even like a TUI. That would be really cool. Like a memory explorer. Voltron. I think GDB might be the best way to explore this. But I think what I'll do is I'll leave it there. So just document kind of what we did. So we dumped the symbol table. And then we can even load this into Ghidra and inspect. And decompile the code to see how these functions are implemented. And then I'll just go over here and say man Ghidra help. Oh, close please. Is there help? I'm just gonna hit save on this. Close this. Oops. Ghidra help? No. Close, please. Oh. That's why. It's being blocked. Okay. Launch.sh. So it does pass the arguments as a project. So I could say Ghidra run or Ghidra and then give it the project here. So it's a Ghidra VDSO dot GPR. File, open project. That's weird. So let's try it again. It says failed to open temp. So the path is wrong. So maybe if I do a relative path to current working directory, it'll figure it out. $pwd. Hey, there we go. Okay. Annoying. So just grab this. Cool. I think that'd make for a little interesting video. I'll record that later today. Let's go ahead and write that out. Say get status, get at all. To see, yeah, looks great. Oh no, I don't want to get status here. There's a lot of stuff I don't want here. Get rm cached VDSO dot rep. Then get ignore. I want to ignore VDSO.rep. And then we're going to rm linux VDSO temp. Rm, yes. Time.1, yes. 2, yes. And the GPR. What is that? Zero bytes. Okay. We'll ignore that too. Okay, we got our get ignore, readme, and main.c. Looks good to me. Cool. Gonna set up this repo here. GitHub. Don't need that or that. Let's go over to here. Or here, new repository. Cool. All right, I'll go ahead and switch back over to the reading thing. And Let's see. All right, I want to start reading on chapter 22 here. Actually, last night I got down to special cases for delivery, disposition, and handling, which is here. So I read all the core dump stuff. There was something I wanted to cat out, was this core pattern, cat proc sys kernel core pattern. And since I'm on system D, I'm pretty sure this is just going to hand the formatting strings over to some system D binary. And that's exactly what it does. So there's a user lib system D core dump, and it just hands all the format strings over to it. And then it does whatever it wants with it. Okay. Feel like I should get maybe a little bit further in this chapter before I take a break. I've only been streaming for about an hour and a half. So let's maybe get to 2 hours, and then I'll take a break for lunch. All right. Special cases for delivery, disposition, and handling. For certain signals, special rules apply regarding delivery, disposition, and handling, as described in this section. Sig kill and sig stop. It is not possible to change the default action for sig kill, which always terminates a process, and sig stop, which always stops a process. Both signal and sig action return an error on attempts to change the disposition of these signals. These two signals can't be blocked with a mask. This is a deliberate design decision. Disallowing changes to the default actions of these signals means that they can always be used to kill or stop a runaway process. Sig continue and stop signals. As noted earlier, the sig continue signal is used to continue a process previously stopped by one of the stop signals: sig stop, sig t stop, sig t and 10, all those. Because of their unique purpose, in certain situations, the kernel deals with these signals differently from other signals. If a process is currently stopped, the arrival of a sig continue signal always causes the process to resume, even if the process is currently blocking or ignoring sig continue. This feature is necessary because it would otherwise be impossible to resume such stopped processes. If the stopped process was blocking sig continue and had established a handler for sig continue, then after the process is resumed, the handler is invoked only when sig continue is later unblocked. If any other signal is sent to a stop process, the signal is not actually delivered to the process until it is resumed via receipt of sig continue signal. The one exception is sig kill, which always kills the process even if that is currently stopped. Whenever sig continue is delivered to a process, any pending stop signals for the process are discarded. Conversely, if any of the stop signals is delivered to a process, then any pending sig continue signal is automatically discarded. These steps are taken in order to prevent the action of a sig continue signal from being subsequently undone by a stop signal that was actually sent beforehand, and vice versa. Don't change the disposition of ignored terminal generated signals. If at the time it was exceeded, a program finds that the disposition of a terminal generated signal has been set to sig ignore, then generally the program should not attempt to change the disposition of the signal. This is not a rule enforced by the system, but rather a convention that should be followed when writing applications. We explain the reasons for this in section 34.7.3. The signals for which this conversion is relevant is sig hup, sig int, sig quit, sig t10, sig t tau, and sig t stop. Interruptible and process sleep states. We need to add a proviso to our earlier statement that sigkill and sigstop always act immediately on a process. At various times, the kernel may put a process to sleep, and two sleep states are distinguished: task interruptible and uninterruptible. Interruptible, the process is waiting for some event. For example, it is waiting on a terminal input for data to be written to a currently empty pipe, or for the value of a system V semaphore to be increased. A process may spend an arbitrary length of time in this state. If a signal is generated for a process in this state, then the operation is interrupted, and the process is woken up by the delivered signal. When listed by PS, processes in the task interruptible state are marked by the letter S in the stat process state field. Task uninterruptible, the process is waiting on certain special classes of event, such as the completion of disk I/O. If a signal is generated for a process in this state, then the signal is not delivered until the process emerges from this state. Processes in the task uninterruptible state are listed by PS with the D in the stat field. Because the process normally spends only very brief periods of time in task uninterruptible state, the fact that a signal is delivered only when the process leaves the state is invisible. However, in rare circumstances, the process may remain hung in this state, perhaps as a result of a hardware failure, an NFS problem, or a kernel bug. In such cases, a kill won't terminate the hung process. If the underlying problem can't otherwise be resolved, then we must restart the system in order to eliminate the process. That seems a little iffy. The task interruptible and task uninterruptible states are present on most Unix implementations, starting with kernel 2625. Linux adds a third state to address the hanging process problem just described: task killable. This state is like task uninterruptible, but wakes the process if a fatal signal, A1, that would kill the process is received. By converting relevant parts of the kernel code to use this state, various scenarios where a hung process requires a system restart can be avoided. Instead, the process can be killed by sending it a fatal signal. The first piece of kernel code to be converted to use task killable was NFS. So NFS was causing issues. Hardware generated signals. SIGBUS, SIGFPE, which is floating point error. SIGBUS is like a hardware failure. SIGIL, illegal instruction. SIGSIGV, segmentation violation. Can be generated as a consequence of a hardware exception, or less usually being sent by a kill. In the case of a hardware exception, SUSV3 specifies that the behavior of the process is undefined if it returns from a handler for the signal, or if it ignores or blocks the signal. The reason for this are as follows. Returning from the signal handler. Suppose that a machine language instruction generates one of these signals and a signal handler is consequently invoked. On a normal return from the handler, the program tends to resume execution at the point where it was interrupted, but this is the very instruction that generated the signal in the first place, so the signal is generated once more. The consequence is usually that the program goes into an infinite loop, repeatedly calling the signal handler. That's neat. Ignoring the signal. It makes little sense to ignore a hardware generated signal, as it is unclear how a program should continue execution after, say, an arithmetic exception. When one of these signals is generated as a consequence of a hardware exception, Linux forces its delivery even if the program has requested that the signal be ignored, blocking the signal. As with the previous case, it makes little sense to block a hardware generated signal, as it is unclear how a program should then continue execution. On Linux 2.4 and earlier, the kernel simply ignores attempts to block a hardware generated signal. The signal is delivered to the process anyway, and then either terminates the process or is caught by a signal handler. If one has been established, starting with Linux 2.6, if the signal is blocked, then the process is always immediately killed by that signal, even if the process has installed a handler for the signal. The rationale for the Linux 2.6 change is the treatment of blocked hardware-generated signals was that the Linux 2.4 behavior hid bugs and could cause deadlocks in threaded programs. The signals demo SIG floating point error C program and the source code distribution for this book can be used to demonstrate the result of ignoring or blocking SIG floating point error or catching a signal with a handler that performs a normal return. The correct way to deal, so you have to do the long jump, correct way to deal with hardware generated signals is either to accept their default action, process termination, or write handlers that don't perform a normal return, other than returning normally. A handler can complete execution by calling exit to terminate the process or by calling sig long jump to ensure that control passes to some point in the program other than the instruction that generated the signal. Synchronous and asynchronous signal generation. We have already seen that a process generally can't predict when it will receive a signal. We now need to qualify this observation by distinguishing between synchronous and asynchronous signal generation. The model we have implicitly considered so far is asynchronous signal generation, in which a signal is sent either by another process or generated by the kernel for an event that occurs independently of the execution of the process, e.g. the user types the interrupt character or a child of this process terminates. For asynchronous generated signals, the earlier statement that a process can't predict when the signal will be delivered holds true. However, in some cases, a signal is generated while the process itself is executing. We have already seen two examples of this. The hardware generated signals and abort, right? I guess raise. You can raise the signal to yourself, kill PG. In these cases, the generation of signal is synchronous. The signal is delivered immediately, unless it is blocked, but see section 2.4 for a discussion of what happens when blocking hardware generated signals. In other words, the earlier statement about the unpredictability of the delivery of signal doesn't apply for synchronous generated signals. Delivery is predictable and reproducible. Note that synchronicity is an attribute of how a system is generated rather than of the signal itself. All signals may be generated synchronously, e.g. when a process sends itself a signal, or asynchronously when it's sent by another process. Okay. Timing and order of signal delivery. That would make sense. That would make sense. Because when I was asked to implement the abort function, the first thing is to raise an exception on yourself for sig alert, I think it is, or maybe sig abort. But yeah, sig abort. But the second step of implementing it is if that is caught by the process, then you have to remove the mask and disposition of the signal, and then re-raise it. And that only makes sense if the signal, or if the code that's doing the abort has sequential execution, where when it raises its first signal, it actually hands over to the handler immediately and then comes back to it when it's done. If it's fully asynchronous, then you can't really guarantee that signal handler had completed running after the first signal was raised. So there are some situations where you can get synchronous signals. So you can use those to implement things like the abort, failover, re-raising stuff. Anyways, timing and order of signal delivery. As the first topic of this section, we consider exactly when a pending signal is delivered. We then consider that what happens if multiple pending block signals are simultaneously unblocked. When is a signal delivered? As noted in section 22.5, synchronously generated signals are delivered immediately. For example, a hardware exception triggers an immediate signal, and when a process sends itself a signal for using raise, the signal is delivered before the raise call returns. Yeah, exactly. When a signal is generated asynchronously, there may be a small delay while the signal is pending between the time when it was generated and the time it was actually delivered. Even if we have not blocked the signal, the reason for this is that the kernel delivers a pending signal to a process only at the next switch from kernel mode to user mode while executing that process. In practice, this means the signal is delivered at one of the following times: when a process is rescheduled after it earlier timed out, i.e. at the start of a time slice, or at completion of a system call. Delivery of a signal may cause a blocking system call to complete prematurely. Okay, that makes sense. Order of delivery of multiple unblocked signals. If a process has multiple pending signals that are unblocked using sigproc mask, then all of these signals are immediately delivered to the process. As currently implemented, the Linux kernel delivers the signals in ascending order. For example, if pending sigint and sigquit signals were both simultaneously unblocked, then the sigint signal would be delivered before sigquit, regardless of the order in which the two signals were generated. We can't, however, rely on standard signals being delivered in any particular order, since Susv 3 says that the delivery order of multiple signals is implementation defined. This statement applies only to standard signals. As we'll see in section 22.8, the standards governing real-time signals do not provide guarantees about the ordering in which multiple unblocked real-time signals are delivered. When multiple unblocked signals are awaiting delivery, if a switch between kernel mode and user mode occurs during the execution of a signal handler, then the execution of that handler will be interrupted by the invocation of the second signal handler, and so on. Yeah, that makes sense. Yeah, it kind of like makes me feel like to keep the signal handler logic hyper minimal, like probably what you should do is just like in the handler, just immediately do a write to a volatile atomic, signal atomic, and then return that out of the signal handler. And then just have something in your main thread or really any thread of the process that is monitoring those globals and taking appropriate actions with normal operating system threads. Like, I understand why they implemented it that way, but I think in the modern threaded world, I would have preferred to just have a separate thread for the handlers instead of interrupting the main thread or any of the threads. All right, we're coming on 2 hours here. This next section is implementation and portability of signal, real-time signals. Got a lot on real-time signals. Waiting for a signal using a mask. Synchronously waiting for a signal. fetching signals via file descriptor, and a process communication with signals, earlier signal APIs. I think that's it, yeah, summary. All right, so that'll probably take a good hour to an hour and a half to get through. So what I'll do is I'll take a break here, and then when I come back, we'll start on the rest of this chapter, and we'll finish chapter 22 next session. And then we're at timers and sleeping, which I'll do this afternoon and this evening. We'll see how far we get. I like to get through this whole thing, so that Wednesday is process creation. But yeah, I'm going to take a break and get some lunch here. So I will be back in about an hour from now, around 1:30 my time. Cool. See ya.